there's an outflux of potassium that leaves the inside of the cell. Okay, because they were just concentrated on the inside, nothing was happening. They've been concentrated on insides of the cell since resting potential, so they didn't go anywhere. So now that they're able to leave on both parts of the axon, they rush out of the cell. As they rush out of the cell, they take with it their positive charge, which means that it helps the inside of the cell to reverse polarity back down to a negative state very quickly. There are two phases that happens here. You have the first phase, which is the absolute refractory period, and then you have the second phase, which is relative refractory period. Okay, I'll show you here. Absolute refractory period is roughly about here. Relative is about here. Okay, so during absolute refractory period, the sodium gates are shut, potassium gates are open, potassium ions are rushing outside of the cell. During this time, it is becoming more negative, okay? Going back down to negative 70 millivolts. During absolute refractory period, during this period, that means that if there is another electrochemical stimulus that is applied to this cell, so another one, we have another incoming stimulus, for example, it will not fire again, even though it has repolarized to this point, okay? Because enough potassium has not rushed outside of the cell yet, okay, in order for it to achieve another action potential, it just, if another stimulus, electrochemical stimulus is applied, okay? But if we wait a few seconds, as more potassium rush out of the cell, it's going to get down to around relative refractory area. That means if there is a strong enough electrochemical stimulus that presents itself, it may fire again. It may cause the neuron to fire again, okay? But that's during relative. So during the second phase, which is relative refractory period, the neuron can fire if the stimulus is strong enough. During absolute refractory period, the neuron has not refracted enough yet, meaning that not enough potassium ions have rushed outside of the cell to bring it closer to negative 70 millivolts yet in order for it to achieve another action potential. So it's not going to fire again at absolute refractory period, but it can fire again if the stimulus is strong enough during relative refractory period stage. Okay. Here's another stop and check for you to do. You can pause here and answer these questions, but I'll keep going. Okay. Propagation of the action potential. Okay. So the action potential happens at every node of Ranvier. Okay. So this is a node of Ranvier. This is a node of Ranvier. And this is a node of Ranvier. I love this diagram because it explains it so well. So here, the first part of the action potential, the first node of Ranvier is where the action potential happens. And if you can see on your end, you'll see the sodium ions are rushing inside of the cell because first at resting potential, it was concentrated on the outside. So they have to rush inside the cell in order to increase the millivoltage up towards the threshold of excitation. Once the threshold of excitation is reached, it's pow, it's going to fire. That's why you see this big bang stuff here. The firing of the neuron here, pow. The sodium that's concentrated on the inside of the cell now travels down the axon. What helps it to travel from node to node really fast is the myelin sheath. Okay, again, a myelin sheath helps to speed up the conduction of the electrical chemical stimulation or the message. So it helps the sodium to travel, pow, shoo, to the next node of Ranvier, which is here, okay? So this node of Ranvier just fired, which brings us down here to the next diagram, because now it's showing how the potassium ions are leaving the axon because it is now refracting. And now this part of the node of Ranvier is depolarizing because at first it was at resting potential. But now that the sodium has reached the next node of Ranvier, it is now depolarizing, which means that the sodium is now rushing into the inside of the axon, okay? So now it fires, pow, shoo, to the next node of Ranvier, okay? So now this node of Ranvier, which previously fired, is now back at resting state. It has refracted all the way back to negative 70 millivolts. this node of Ranvier is now refracting, and you can tell because it shows the potassium leaving the inside of the axon. And this node of Ranvier is now depolarizing and is now firing. Okay, so as I was saying before, the node of Ranvier is very important because that's where the firing takes place. It has to fire, the neuron has to fire at every single node of Ranvier in order for it to carry the strength of the charge. Well, I should say, in order for the strength of the neurochemical charge to reach one end of the axon to the other end of the axon. If you think about like a giraffe. So say, for instance, a giraffe has, in the giraffe, you had the dendrites at the head, and then at the axon, what is a giraffe, about 17 feet tall, 12 to 17 roughly. So the electrochemical message actually goes from the head all the way down to the presynaptic terminals, let's just say is at the giraffe's foot, okay? So if the axon was not myelinated, that means that it would fire, but if it has to go roughly 12 to 17 feet, it might, the charge, we're talking about electrical charge here, it might fizzle out by the time it gets to the giraffe's foot, and it wouldn't be able to send the electrical chemical message to its neighboring neuron at the toe. So in order for the stimulus to reach its targeted neuron, its next neighbor, no matter how far the distance is between the axons, between the neurons, due to the length of the axon, it has to fire at every node of Ranvier. Pow, 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 until it gets to its destination, until it reaches the end of the presynaptic terminals. So it makes sense. The body is very intelligent, okay? So that's why the node of Ranvier, these little spaces, these little gaps in between the axon is so important. So the electrical chemical charge can reach the end of the axon, okay? The next slide, these I have on here as helpful sites. One is it shows you a step-by-step interactive tutorial of how the whole process that we just went over, the firing of the neuron, how all that takes place. Okay, so you can click on this site, and it's a great tutorial. It'll go over every step as slow or as fast as you want it to. It's kind of like a little stage play, but animated. Most students really like it because it helps them to explain. It helps to explain what I just went over. Not really more in depth, but slower. And then the Neuroscience for Kids is a site that I use, and just in case you want more information about neurons and brain areas, and even throughout the semester you can use this site, Neuroscience for Kids. Okay, so these are readily available. I would really use this tool right here, the animated video, to help you to understand the neuronal firing. Okay, so this will conclude chapter 1, and I will see you next week for chapter 2. Have a nice weekend.